Welcome all to lecture 9 of subsurface exploration, importance and technique involved. So far we have discussed about different classification of investigations, then we started with direct methods like test pit, trial pits, trenches, then we went to semi-direct method, that is mostly geotechnical investigation, different kind of geotechnical investigation we had discussed earlier like standard penetration test, cone penetration test, dilatometer test, pressure meter test and so on, vein shear test, what are the advantages, disadvantages of each of those tests, and then we have also solved typical numerical problems like how to interpret field records in order to identify the soil type in order to determine different properties of the medium. So, as we know, like most of the geotechnical tests are point based methods, like whatever soil type you are determining, it will be at that particular location and at that particular depth. However, whenever we are interested to find out subsurface properties of a particular site, we are interested to find out what is the lateral variation. At times we are interested to go for deeper location probably where geotechnical investigations are not feasible. So, considering the requirement for interpolation, considering the limitation with respect to depth exploration, at times moreover in addition to that, like whenever we are going for any kind of geotechnical testing, it requires lot of time, expertise, as well as because it requires lot of time and specific equipments. Most of the time geotechnical tests are expensive and time consuming. So, because of these three major limitations or issues, and in addition you can explore particularly when larger area is there where the required number of tests are significantly larger, you have to invest more number of time and huge amount of finance also, particularly when you are going for geotechnical investigation. So, another option which comes to mind which is not new, but even the techniques which people are following nowadays, even for smaller areas, for regional study, even for local study, site specific studies. So, more and more methods have been evolved in last 1 decade, even though because of use of geophysical investigation, particularly for oil exploration, mineral exploration and even for geological explorations, it has been in use for quite some time, maybe for 3-4 decades now. But more and more use of geophysical investigation has become more prominent nowadays, because such investigations can be done even at local scale, and because of improvement in the interpretation, because of the significant reduction in the initial investment regarding the setup purchase, it has I mean now the geophysical investigations are people can afford that. That's what I want to say here. So, from today's lecture onward, we will be discussing about what are geophysical investigations, and we will be discussing, just like geotechnical investigations, some of the geophysical investigation methods. What are the methods, how you interpret the typical field records in order to quantify the subsoil properties. So, as the name suggests, geophysical investigation, we are interested to find out, we are interested to quantify the soil type, we are interested to quantify the subsoil properties, physical properties of the medium based on some ways of using geophysics. So, it comes under module 3 as lecture first lecture, or overall it is lecture 9. So, it consists of determination of subsoil information, which is the broad objective of this course. From test pits as well as geotechnical investigation, it is time consuming as well as expensive, as I highlighted earlier. Moreover, earlier discussed tests are generally conducted at limited location. So, whatever your site of interest, depending upon the guidelines provided for different kind of structure, for different kind of field investigation, even for different kind of seismic zones and areas, geotechnical investigation can be the entire area can be divided into number of grids, and for each grid you have to conduct at least one or more than one test. At times you have to validate the findings from geotechnical test by one more test. So, that we have discussed. But what about if the properties are varying in between the grids, like you did the test at two location and consuming and assuming like either it is same as if it is not changing between the two test location, or whatever change is happening, it is happening linearly. So, in those cases where interpolation is required and considering the finance involved, you have to go for limited number of geotechnical tests. So more your field investigation or interpretation part will be depends upon interpolation between the field tests. So, in those cases also geophysical investigation, because there you can actually explore a larger area, you can even go for continuous recording, you can even go for 2D two-dimensional methods also, where you can have complete information about how lithology is changing in terms of depth, in terms of physical properties along the survey line. So, that is another important aspect when we go for geophysical investigation, like those are less time consuming as in comparison to geotechnical test, and interpolation is also significantly easier, or most of the time you can, rather than going for interpolation between two test locations which are wide apart, you can go for more number of tests, because these are relatively quicker methods. So, geophysical test being indirect method, because you are not actually not getting any kind of soil sample from the depth, or you are not taking out the sample, or any kind of sensor you are not going to lower there. So, mostly these are called as indirect method, because you are putting the sensor at the surface, any kind of disturbance which the sensor is detecting, even that kind of disturbance is also located at the surface. So, these are called as, that is why non-destructive test, and thus lesser time consuming, because you need not drill a borehole, you need not drill a trench. So, you can simply put some sensor at the surface, and by means of some typical measurements at the site of interest, you will be able to understand what kind of soil properties are there at the surface, what kind of soil properties are there below the depth at different layers, and depending upon what kind of depth you are interested to find out, you are interested to explore, you can go for different kind of sources, you can go for different choices of receivers as well. So, these are overall less time consuming. It can be done over larger areas, you need, because these tests can be conducted over larger area, because your sensors will be spread over larger area. You can go for tests even in 2 dimension. So, you can actually go for these kind of tests over larger lengths without interpolation, because that will be consist of almost continuous recording. So there will not be any much requirement for interpolation in between. What it does, it depending upon the physical properties of the medium, see, like the kind of depending upon which kind of test you are using, the geophysical test, each geophysical test will be able to determine some variation in the physical properties of the medium, either using those physical variation directly, or by using some correlation, empirical correlation, you will be able to determine what kind of soil deposits are there, what are the strength characteristics of the soil deposits, which will be thereafter you can use it for subsurface exploration, for interpretation, for foundation design, even for dewatering purpose also, and so on and so forth. You can use it depending upon what is the choice of geophysical method you are using. So, it measures the physical properties of the medium, so that you can go for subsurface characterization, even you can go for identification. Like at times it is not only used for identifying different layers, it can also be used for identification of buried object, it can also detect some unconformity, it can also detect some like in archaeological survey also geophysical tests are very prominently used. So, that you can actually able to find out, because without going for any destructive test, because those are very important site, you cannot blindly keep on destructing the existing structure, so that you can explore at deeper depth. You can go for non-destructive test and find out what are the buried objects, hidden objects which are to be excavated out, and it can be bring to the public, I mean it should be exposed to the public. So, I told you like geophysical tests are very useful whenever exploration is required, whenever interpolation is required, whenever deeper depths are required for exploration. Very useful nowadays geophysical test for particularly for microzonation studies. Like microzonation, as we know, like most of the time whenever we are interested to find out what is the inertial force because of seismic activity in a particular region, nowadays people are going for more and more regional studies, or site specific study, or even building specific studies, in order to find out what is the seismic activity, what is the potential seismic hazard, what is the potential level of ground motion which is expected at my site of interest. further those ground motion will be altered because of the presence of local soil. So, in order to take into account the variation in local soil properties at your site of interest over which your building is located, geophysical tests are more and more nowadays people are practicing, so that you can quantify the subsoil properties. Once you know the subsoil properties, you will be able to identify how these subsoil properties are dominating in controlling the seismic vibrations into a building. Then second thing, quality control. Like your designer suggested some minimum density of the medium at the site of the interest, even whenever you are going for subgrade laying or you are going for any kind of filled up area. So, once the site is filled up, you can actually go for some kind of quality check. You can do some tests, and based on that, in the test it will be able to determine what is the strength properties, what are the densities of the medium, so that you can match those densities which you are getting from geophysical test with the density provided by the designer, in order to ensure like your quality, like the guidelines which are given for filling up the area for preparing the subgrade, are those being properly matched. So, it is like quality control. Third one is forensic investigation of failed structures. So, whenever there is some kind of failure at the structure, particularly like abutments of bridges, flyovers, retaining structures, you can actually go for forensic investigation in order to find out, because those structures are already failed. At times it is not advisable to go for detailed geotechnical investigation, because again that can trigger more distress to the existing structure, though it is already failed. You can go for geophysical methods, so without creating much of disturbance to the surrounding area of any disturbed or failed geotechnical structure. You can go for you can explore the subsoil property and find out whether there was some problem during laying of subgrade, whether there was some problem during filling for preparation of abutment, approach road, or any preparation for zone of influence for any bridge piers, and so on and so forth. So there are number of varieties of ways in which forensic investigation for failed geotechnical structure can be done very easily, considering the non-destructive nature of geophysical tests. The next one is validation of the findings. At times, whatever geotechnical investigation you are doing, you can also validate, so that if a particular geotechnical investigation has limitation with respect to the depth, you can go for geophysical investigation for deeper depth. So that way you will be able to develop some correlation between some measure of geophysical test, some measure of geotechnical test, and that's how you will be able to determine the outcomes of from geophysical test at deeper depth, in order to find out the equivalent properties in terms of geotechnical testing. So this is like validation as well as interpretation. Then it is suitable for deeper depths, where many geotechnical tests might not be possible to perform. So each and as we know, like SPT test, CPT test, dilatometer test, each of these tests has some limitation in terms of the depth of exploration. So if your depth of influence is more than that particular depth of exploration, there must be some other ways with which you will be able to determine what kind of subsoil properties are there, what are the physical properties of the medium, what are the soil types. So in those cases also, particularly for deeper depths, geophysical investigations are very important. The common methods, as I mentioned here, like in earlier times, people were going for more and more for like gravity survey, magnetic anomaly methods, then seismic reflection methods for mineral exploration, for studying the geomorphology of the area, even for studying the geology or topography of the area. People were going, and even for oil exploration also. So people were going for more and more for these methods. But over the period of time, more and more advancement in the technology and more sophisticated and user friendly equipments are nowadays available. So you can see here, I have given here the list of different geophysical methods which are more prominently people are using nowadays, starting with seismic reflection survey, then seismic refraction survey, electrical resistivity survey, sounding and profiling survey, magnetic anomaly method or magnetic anomaly test, gravity method, suspension logging method, and then we will also give some brief idea about what is multi-channel analysis of surface wave, that is MSW, and spectral analysis of surface wave, that is SSW. Those two tests are more and more prominently people are using now for forensic investigation, even for quality control, even for microresonance studies. So, we will be discussing overall like these are the list of prominent tests which comes under geophysical testing methods. As far as the syllabus of this course is concerned, we will be discussing about seismic reflection test, seismic refraction test, electrical resistivity method, magnetic anomaly, gravity method, suspension logging, and as I mentioned here, when we will be discussing about other method, I will give also some glimpse about what is MSW, what is SSW. Now, coming over to as I mentioned here, like geophysical test has certain advantages, certain limitations. So, I am going to list out here what are the advantages. So, what it does actually, it tries to find out based on physical medium, based on physical property variation, or you can say when there is too much of contrast, in characteristics of the medium, what it does, there will be too much of variation in conductivity of the medium, whether it is related to reflection, refraction, whether it is related to magnetic property of the medium, whether it is related to electrical properties of the medium. So, it keeps on it keeps on interpreting the physical property of the medium by the change in its field record characteristics. Suppose you are going for, because of too much contrast, you have to be very careful with too much of contrast. So, like you are going for any kind of field test, you know, like at the site of interest there are different layers. One may be very soft layer, one may be very stiff layer. So, when a particular, like you go for seismic method, when any kind of waves will be there, when it will reach the interface, when the wave will face too much of contrast, that will show too much of change in the properties of the medium. So, because of this too much contrast, maybe in terms of wave velocity, you will also interpret, okay, there is change in the medium characteristics also. So, geophysical test targets for identification in the physical properties variation because of change in field record characteristics. So, advantages include, you can go for deeper depth, you can go for almost limited interpolation, because you can go for limited interpolation, then you can go for, these tests are quick and less time consuming. Then you can go for less time consuming, limited interpolation, and then can validate findings from geotechnical test. At disadvantages, I can say here limitation, requires, most of the time these tests are significantly costlier, you can say here costlier, require trained people, because interpolation is required, at times require larger area for investigation, for setup of instrument, and keep in mind these are indirect methods. So, indirect, so always reliability of field recording and interpretation is to be validated. Like you have to get more and more confidence, whatever interpretation you are doing, it is correct. Then another advantage here, you can do those tests over larger distances. So, that is why very much similar to your geotechnical investigation, you can say here one note you can put, suggested like at least more than one method of investigation should be used. Even in geophysical method, you can go for at least more than one method. Either you can go for additional geophysical method or you can go for geotechnical method, so that findings whatever you are getting, it will be validated. I had mentioned here different methods also, like seismic reflection survey, seismic refraction survey, electrical resistivity, magnetic anomaly methods, gravity test, suspension logging, then multi-channel analysis of surface wave, spectral analysis of surface wave, so on and so forth. Now, we will be discussing here onwards what are the seismic methods, because as I mentioned here, the first two methods are called as seismic reflection survey or seismic refraction survey. So, what do you mean by seismic methods? Why it is called as seismic methods? We know, like because of any kind of disturbance which may be because of impact load, maybe because of explosion, maybe because of machine operation, maybe because of waves in water, that is water currents, there will be some kind of disturbance or some kind of shock. These will result in development of some kind of shock or shock waves, which will travel as well as cause disturbance in the propagation medium. So, depending upon which medium it is passing through, it will cause some kind of disturbance. Now, what kind of disturbance it is going to cause, that depends upon what kind of wave you are targeting for. So, precisely you can tell, like whenever there will be some kind of shock waves, whenever there will be some kind of disturbance because of above mentioned reasons, there will be different kind of, the disturbance at the surface will cause some kind of wave generated at the source. Like if I am showing here, like this is your source, which can be anything like explosion, it can be impact load, it can be a machine operation, it can be even passage of traffic also, it can come here, like traffic movement. Each of these can cause some kind of shock. So, I am referring source to any kind of this disturbance, as a result of which what will happen, wave will be generated. I am showing here some kind of wave fronts. So, wave front means whatever material is available at this particular location, it will be undergoing some kind of disturbance, and depending upon how much the resistance against this disturbance the material offers, that will help in understanding, quantifying some measure of material property. What I meant to say, if the wave is passing too quickly, we can say the material is stiff or it can be hard, because the resistance offered to the material is significantly high. If the material is passing very high velocity, you can call it as stiff material, hard material. Same way, If it is very slow velocity, you can call it as soft material or softer material. So, what is happening as a result of this source, any kind of disturbance, wave is actually wave fronts are creating. Now you can see here, this is at the ground level. Okay. Suppose this is soil layer 1. I do not know whether this soil layer is sand, clay, or it is soft medium, it is harder medium, because most of the geophysical methods give you quantitative assessment, and this is your soil layer 2. Now, when we went for trenching, when we went for test pits, when we went for geotechnical tests, we were interested to find out what kind of soil layers are there, what is the measurement of strength properties. Even here also our target will be to determine what is the thickness and what is the, you can call it as some ways of measurement of the physical properties, physical property of this particular soil layer. Now, what will happen as a result of this wave front? I am showing you some partial this thing here. So, once the wave front reaches there, at the interface, why I am calling it this as an interface? Because this medium, suppose this is very stiff, soft medium, this is stiff medium. Because of the sudden change or too much contrast in medium characteristics, what will happen? The incident wave, either some wave, first of all some wave will be travel along the surface, this will be called as direct. Some wave, you can see here based on the wave front, will reach at the interface and will reflect back. Some wave might travel to the deeper medium, so you can call it as either absorb, or you can call it as travel downwards. Some wave will travel along the interface, which keeps on creating more and more wave fronts, because once it is traveling here, again it will be considered additional source, which will again transfer. So, I am putting here another receiver, which is actually going to detect what kind of disturbance, whether you are getting from here. So, depending upon at which particular depth this too much contrast or the interface is there, too much contrast in the medium, or you can call or interface. So, whenever the interface comes, what will happen? The wave which is you can call it a shock wave, which was generated because of any kind of disturbance caused at the source. Once the wave reach at the interface, it will experience some kind of too much contrast in the medium characteristic, as a result of which some energy the wave was carrying, it will be absorbed in the material that is traveling downward. Some will travel, some will reflect back and travel start traveling towards the surface, which will be getting detected by the receiver. So, depending upon you see here, because of the wave front, it is causing some kind of disturbance in the material. So, depending upon what kind of disturbance, the nature of the disturbance caused in the material, or the kind of movement, this material, that is soil particle in this particular case. So, nature of soil particle movement, that will help you in understanding what is the characteristic of this medium. So, generally based on, there can be different kind of waves which are getting, which are possibly generating, which can possibly be generated from the source, and depending upon the nature of each kind of waves, it will be causing different kind of soil movement. So, I am telling here, nature of the soil particle movement will change, will vary from wave type to wave type. Wave type to wave type. So when we discuss about seismology, when people started interpreting about different layers of the earth, it is understood like precisely the kinds of wave which are generating because of any kind of shock can be classified as, I am calling here shock, like the shock which can actually cause some kind of disturbance to the material. So we can precisely classify it as P wave or primary wave or compressional wave which are causing compression and rarefaction to the material. You can call it as P wave. Then secondary wave or S wave or shear. These are, so first one was causing compression and rarefaction. This is causing some kind of shear, you can call it as shear wave. So you see here, when a primary wave is passing through the medium, it is causing some kind of compression, expansion, compression, rarefaction, like compress and then it will bring it to its original position. So with respect to second position, it will be expansion, but finally it will come to its original position. Then second one is shear wave. So whenever the wave is passing, like this is the direction of wave propagation, direction of wave propagation. So what it does, once it is shear wave, it will be causing shear in mutually perpendicular direction. So particle motion will be either perpendicular to the wave or the other one will be perpendicular to this board. So this, depending upon what is the in which plane the shear stresses are getting developed, or when, in which plane the particle is undergoing some kind of shearing, it is called as SV or called as SH wave. But both of them are causing, it is happening because of passage of shear wave. So in order to, when shear wave is passing, the material is offering resistance in terms of shear strength of the material. And the third one is Rayleigh wave, which is precisely caused when this body waves interact with the superficial layer of the earth. So these are called as Rayleigh waves, or it causes elliptical motion in the soil particle. So whenever the wave, particularly the Rayleigh wave is passing, the particle motion will be like this. So there will be some kind of elliptical motion. The last one is called as Love wave. Here the particle motion will be translational, or like side wave motion will be there. These again are classified as surface waves because more prominent and near the surface of the ground. So these are precisely four kinds of wave. Whenever we go for seismic methods, these are precisely four prominent kinds of waves. Again, you can have other waves which are mostly generated because of reflection happening from heterogeneities present in the medium. Like there can be any local pockets which is available in the medium. So whenever that local pocket is there, again that will be considered as additional source of disturbance or additional source from which the waves are getting reflected or some energy is getting contained. So this will be again recorded at the receiver at later stage. Those are again called as, those waves are called, to give you an example, those are called coda waves, which are generating because of the heterogeneity present in the medium. Whenever we go for interpretation, we generally consider any soil layer, this is homogeneous. So whatever material property you are getting, it is like applicable throughout the material, unless there is too much contrast or there is too much change in the medium characteristics. Otherwise, up till that depth till which there is not too much contrast in the material, the entire material will be characterized as one kind of medium. So this is like, so you will be able to, whenever we are interested to go for seismic method, we are interested to find out based on this, we are actually inducing some kind of vibration, and depending upon what kind of disturbance it is creating, we will be interested to record those disturbance, and depending upon the characteristic of time of arrival of those disturbances at your receiver end, you will be able to interpret the physical property of the medium. Now one question which comes to mind is how you quantify which kind of wave you are actually determining, like you have put the receiver, but receiver whether it is recording P wave, whether it is recording S wave, whether it is recording other waves. So that depends upon what kind of disturbance you are actually creating at the source. So whenever you are going for vertical impact load or explosion, mostly your shock will be dominated by P wave dominant. So if you put a receiver and this is your shock or this is your source, mostly it will be containing your maximum content or maximum energy will be transferred through P wave. Similarly, if you are taking some horizontal striking of a rod, mostly it will be contained by S wave dominant. So if this kind of disturbance is there where you are actually some rod is there which you are striking horizontally against any lateral movement, resisted or restricted against lateral movement. Otherwise, if lateral movement is there, then it will not cause much. I mean, most of the energy will be confined to the surface itself, and it will not cause any kind of disturbance or any kind of shock waves or shear waves at deeper layers. So this is like when we are interested to find out, when we are interested to determine P wave velocity, we can go for vertical impact or explosion. When we are interested to find out S wave velocity, you can go for accordingly, like depending upon what kind of source is there, you can decide which kind of wave will your receiver is detecting here. Now, as I have been mentioning here, because this is method of exploration, so depending upon your velocity of the medium, we call it as Vp, that is primary wave velocity, this is called as Vs. So depending upon what kind of material is there, I am going to give you here some chart and then the value of Vp in kilometer per second. So let us see what is the overall velocity of primary wave of propagation through different material. So to give you an example, if air is the medium, the primary wave travels at a rate of 0.3 kilometer per second, which is almost close to the velocity of the sound. When we go for water, the primary wave velocity increases from 1.4 to 1.5. Similarly, ice, this is like for different medium, what is the primary wave velocity, which if some seismic recording station is there, you will be able to detect the primary wave because of any seismic activity happening in the other parts. Then clay, you can have primary wave velocity from 0.5 to 2.1. Then sand, you can have primary wave velocity from 0.2 to 2.0. Then granite, you can have primary wave velocity as high as 4.5 to 6.0. If you remember, granite we had also discussed, like this is very intact rock, so it is offering more and more resistance to any kind of primary wave passage or any kind of movement which the primary wave offers in terms of compression or rarefaction. That is why the primary wave velocity is like this. So based on seismic method, if you are able to quantify your primary wave velocity is in this range or this range or this range, that is giving you an indication that the medium through which this primary wave is propagating and getting detected by the receiver, this medium is either granite, sand, clay and so on and so forth. So that is how you go for interpretation of subsurface medium. You try to measure some way the physical properties of the medium, and then depending upon what is the range of physical properties of different medium, directly, particularly when you are going for seismic methods, or indirectly when you are going for other geophysical methods, you will be able to identify what is the medium, what kind of medium is there, what are the physical properties of the medium, and at times what is the depth of the medium. So this is again, as I mentioned here, like each of these properties are related to physical properties of the medium. So let us see how these like Vp, that is primary wave velocity, it can be related to the elastic constant like K plus where K is bulk modulus of the medium, this is G is shear modulus of the medium, rho is mass density of the medium. So, based on this you can understand whenever primary wave, your primary wave velocity is giving you indication of some other physical property, the elastic constant of the medium, and Vp is P wave velocity. Same way you can quantify, because shear wave is causing disturbance in terms of shear, like shear failure. So, it is directly related to your shear wave velocity 1, 2. So, Vs is your S wave velocity. So, in the previous table I had given you the range of primary wave velocity for different mediums. Same way you can determine the shear wave velocity of the medium. Third is Vp by Vs itself can be correlated to so that is how Vp and Vs ratio of a medium is related to the is almost constant, where this is called as Poisson's ratio. So, this way you will be able to determine, once you know one value, you will be able to determine based on the recording time of the kind of wave, the wave which is being dominated by the source, depending upon what is your choice of the source, you will be able to determine Vs value, Vp value. Once you know both the values, you can determine Poisson's ratio or vice versa. So, just by measuring this travel time of travel or time of arrival of different kind of wave at between the source and the receiver, you will be able to quantify what kind of medium is available. Now, let us see about seismic. So, in order to go further into detail, we will be discussing about what is seismic reflection survey. Seismic reflection we will be discussing in next class. Now, as I mentioned earlier also, we are interested to find out what is the thickness of the medium, we are interested to find out what is the P wave velocity of the medium, and because for any disturbance or any reflection to take place at the interface, I am considering this interface is indication of too much contrast in the medium characteristics. I am writing here interface. Otherwise, interface is not there, or if the medium contrast is not significant, what will happen? This boundary will shift downward unless there will be boundary for too much contrast in the medium. Now, I am keeping a receiver source here, which can be explosion, it can be vertical impact. I am keeping a receiver here, very much similar to the previous slide. So, because of this, there will be wave fronts okay. So, like this wave front, once it reached here, again some portion of energy will be reflected back. I kept here I mean keep in mind, like the angle of incidence here will be equal to the angle of reflected wave, because it is reflection. So, the angle of inclination will remain same. So, this is known as reflected wave. This is called, so in addition to this, there will be some kind of wave which is travelling along the surface, which is called as direct wave. So, at the receiver, if you see the receiver, you can see two kind of disturbance. First one will be the arrival time of direct wave, and then it might minimize, and then again you will have second peak, which will be like arrival time of reflected wave. Now, I am giving you a signature of receiver signal. This is very simplest form. As more and more actual field condition keep on adding here, this will become more and more complicated. So, I can sell it simplest form of receiver signature. Now I am trying here, so I will be interested to go for 2 recordings of time at receiver one is time of arrival of direct wave. So, when your receiver detects direct wave time of arrival, that will be called as T suffix D. Second one is time of arrival of reflected wave. That is T suffix R. Now you see here, if you are for a known distance between the source and the receiver, that is capital L, what will be the Vp value, that is Vp1 for layer number 1. Vp1 can directly be called as L over Td. Like for known distance between the source and the receiver, if you know what is the time of first disturbance to be detected at the receiver, you will be able to determine what is the value of Vp1. Now you see the second one, you are interested to find out thickness of the medium. So the time of arrival of reflected wave is a function of, so you say it as O A B, that is called as OA plus AB, that is the length divided by Vp1. Vp1 is the propagation path velocity. So, this PV velocity along the propagation path of reflected wave between the source and the receiver. Now, this can be called as, so OA and AB are equal, you can call it as 2 times AB divided by Vp1. Now, because this incidence angle is equal, so this length will be L by 2, this another one will be another L by 2. So, you can call it as 2 times. So, this one you are interested to find, suppose this is OA, you are interested to find out, that is AB equals to, so this will be L by 2 whole square, considering this as COAC as right angle triangle or ACB as right angle triangle. So, L by 2 square plus H square, that will be the length of AB divided by Vp1. Take this 2 inside the square root, so that will be L square plus 4H square square root divided by Vp1. So, Tr. So, for known values of Tr, L, Vp1 known. So, this is equation number 1, this is equation number 2. Your value of H can be determined from equation, estimated from equation 2. So, just by means of one source, one receiver, based on detection of time of arrival of direct wave, time of arrival of reflected wave, that is Tr and Td, you are actually able to determine what is the P wave propagation velocity. Based on your P wave propagation velocity, you can quantify whether your medium is sand, silt. Of course, you can better classify in terms of stiff medium, soft medium, hard medium, and then you can also determine what is the thickness of the medium. So, this is the overall thickness of the medium. This is called as seismic reflection method. So, let us solve one numerical example here in order to understand better, like what is the way you can actually quantify this medium characteristics. So, the numerical is like a loose deposit of over consolidated clay is underlain by bedrock. Okay, just before solving this numerical, I would like to highlight, like the numerical problem which I showed earlier, it was related to this, the derivation which I showed you here, it was considering relatively leveled ground. Same way, if you go for inclined surface, so where this is the source and this is your inclined interface. considering at an angle alpha. So, this problem here also you are interested to find out what is the thickness, what is the soil type here, what is the thickness. So, thickness maybe I can tell you here d alpha, what is the inclination here. This can be solved by keeping the source and receiver. So, two receivers actually you can keep, one on one side, other receiver you can keep either here or you can keep here itself. Again you will be having two measurements here. So, this is d alpha is the depth of investigation at where you have kept both the receivers and the source. So, suppose TRS is the time of arrival of reflected wave when receiver and source at same location. If you know this, you will be able to determine what will be the value of d alpha, that is equals to TRS divided by 2 times Vp1. Vp1 you can determine, if you know the value of this, that will be equals to L. So, Vp1 again based on detection of direct wave arrival, that will be called as T over T direct at receiver. So, that will be called as TDR. So, using first one, I am calling this one as first one because based on this you will be determining first the Vp1 value, put that Vp value there and you will be able to determine what is the d alpha. Now, sin alpha you can determine. So, that will give you what is the angle of inclination, you can determine based on the formula which is as Vp1 square T, that is time of arrival of reflected wave, that is time of arrival of reflected wave at receiver plus time of arrival of reflected wave direct wave at the source when both are kept at the source and the receiver, then TRR minus TRS minus L square over 2 times T R oblique S times Vp1 times L. So, TR this is called as the time of arrival of reflected wave when you kept the receiver at the source itself. This is the time of arrival at the this receiver, okay, I can call it as receiver 1 R1. So, time of arrival of reflected wave at receiver 1, time of arrival of again reflected wave when the source and receiver are kept at same location. L is the distance between the source and the receiver 1. TRS is the time of arrival between the source and the first source and receiver both are kept at the same location. So, that is how you can determine the value of alpha. Once the value of alpha, value of d alpha, once value of Vp1 all are known, that will help you understanding how variation of interface layer is taking place and what is the physical property of the medium. Okay, so, this is a numerical problem. A loose deposit of over consolidated clay is underlain by a bedrock. Previous investigation, subsurface investigation in the area suggests that the bedrock is almost horizontal. So, almost horizontal means you have to take up the first example where the bedrock was almost horizontal and then you determine the thickness as well as shear velocity, primary wave velocity of the medium. During a seismic reflection survey, the receiver marks the arrival of waves as 41 millisecond and 267 millisecond. So, based on the difference between the two values, you can understand the first arrival will be direct wave, second arrival will be for time of arrival of reflected wave. As a result of impact loading which is kept at 37 meter from the receiver, determine P wave velocity, thickness of soil layer and also using the Poisson's ratio of 0.3 determine the value of S wave velocity. So, this is a problem. So, how we will solve this problem? First of all, write what are the things given here. What are given here? So, we have time of arrival of reflected wave, that is 267 millisecond, time of arrival of direct wave which is given as 41 millisecond. Remember, with be careful with the units, and then distance between the source and the receiver which is given as 37 meters, and Poisson's ratio which is given as 0.3. We are interested to find out Vp, H and Vs. You can call it as 1 also, because one layer is there. So, going with the derivation which we did for seismic reflection survey first part, when the bedrock is horizontal. So, first one will be Vp1, that will be equals to L divided by Td, that is 37 divided by 41 is given in milliseconds. So, you can convert it to seconds. That is how you will get to know what is the value of Vp, that is 902.44 meter per second. Now, second one, you are interested to find out the thickness. So, you can directly determine the thickness, that is H, you can determine as Tr equals to square root 4 times H square plus L square over Vp1, that is square root 4 into H square you have to determine, plus 37 square over Vp1 is 902.44. So, you solve it, and this Tr value is given as 267 into 10 raised to the power minus 3. So, if you solve this equation, you will get to know the value of H equals to 109.04 meter. The third part is determination of Vs value. So, we know like Vp over Vs is given as 2 times 1 minus nu over 1 minus 2 nu raised to the power 1 by 2, nu is given as 0.3. So, you will be able to determine the value of 2 times 1 minus 0.3 divided by 1 minus 2 times 0.3 raised to the power half, that will come as 1.87, that is Vp by Vs. So, Vs you can call it everywhere 1 also, Vs1 will be called as Vp1 over 1.87, that is 902.44 over 1.87, that comes out to be 482.59 meter per second. Be careful with the units, otherwise you will end up in, though you will report your value in meter per second, but your time of arrival is given in milliseconds, because this is considering the layer thickness of just 119 meter, it will and considering the Vp velocity of 300 meter per second and of that order. So, it will take more time for I mean it will take relatively lesser time, rather it should be quantified in terms of seconds. So, with this I hope this example and then today's class had given you sufficient idea like what is the source, what is the receiver, and depending upon the choice of the source what kind of wave will be dominating, what will be the how the energy contained or generated at the source will be contained to the receivers depending upon the choice of the source. And once you know the choice of the source, depending upon the time of arrival detected at the receiver, you will be determining corresponding either P velocity, S wave velocity, and so on and so forth. So, that is how you can determine, and then based on the numerical solved, we are you can understand how you determine how you interpret the properties of the medium. So, you can determine the Vp value, Vs value, Poisson's ratio once it is known to you, or if you are able to detect Vp and Vs both, you can determine the Poisson's ratio itself. And then once you know the medium density also, which probably you can determine from geotechnical test, you can also determine the value of shear modulus, bulk modulus, and other things. So, thank you all.